In this portion of the lectures, we're going to discuss chaos and nonlinear dynamics. So let's give a brief introduction, and then we'll look at a nonlinear system that's not a biomedical system, but we'll look at it because it's easy to understand what's going on. So, as way of an introduction, we want to describe three different kinds of signals: stochastic signals, deterministic signals, and chaotic signals, and what their differences are. So a stochastic signal is one that consists of random variables. We often think of the EEG to be a stochastic signal because if we were to look at its property, we would see that often the distribution of whatever variable we're looking at follows a random statistical process. A deterministic signal is one that can be defined by an equation or a set of equations. Now, these may be complicated equations, they may be very high order equations, but we could eventually reproduce a deterministic signal if we were able to find the correct defining set of differential equations. And then finally, a chaotic signal is one that appears to be random, but in fact, it's actually not random. It actually does have some structure, but this structure is often hidden. It's difficult to determine. It's highly dependent upon initial conditions. Initial conditions play a lot into the behavior of the system. So these three types of signals are um, typically in most signal processing classes. We look at stochastic signals or sometimes deterministic signals. Rarely are chaotic signals looked at, when in fact most of the time, most processes within the human body and within nature are in fact chaotic. So before I go to screen view mode on the PowerPoint presentation, I want to go to this little short YouTube video where we're going to look at an example of a chaotic process. So let me go to the internet. This is going to be the YouTube video. Before I let it run, let me point out that we have some water dripping here. Okay, the flow rate can be clearly controlled. This water wheel is a clear physical system, so we know, for example, exactly how much water each cup will hold. We could model the physics of the system based on weight and looking that it's got some rotation. So theoretically, we can define all of the aspects of the system. So let's see what happens as the water wheel runs.
Doing another video.
Yeah. So you can see what's happening here is as the water drips, you've got some oscillation going on, but it's not any kind of, there's not any kind of repetitive nature to it because it basically is changing as the water, in fact, you can see now it's just sitting here, not a lot of movement at all, water's running, it's filling the cups, and now all of a sudden something happens and the wheel goes crazy. And no real way to predict what direction that was going to rotate in. It just, could be due to any number of things, including where random droplets of water fall. But theoretically, if a person was good enough at the physics, you could write a set of equations that would actually govern the behavior of the system. So this is a classic example of a chaotic system. We probably have some others here. Haven't looked at this one yet. This is, I guess, the Lorentz fire wheel. Lorentz is a classic chaotic system. So we have some candles here, and you can see kind of based on how much wax drips off of each candle, the weight distribution of this rotational system will change, and so the way the rotation goes and both the position and the rotation velocity are changing, and they're fairly random, or appear to be random. They appear to be changing in a random way. Then you can see we're sitting here for a very long time. Eventually, as wax drops more off the bottom candles than the top candles, this will become top heavy, and we'll see some rotation again, hopefully before I turn this off. Yeah, there we go. So some additional rotation. So these are good visual examples of chaotic systems. So coming back to PowerPoint, and let's see here, let's go into screen show mode. I'm not super familiar with Microsoft 360, 365. Okay, so in addition to talking about stochastic, deterministic, and chaotic, we can also talk about whether a system is linear or nonlinear. And we talked about this some before. As a general rule, when you look at things in the frequency domain, you use Fourier analysis, you use wavelet analysis, you use any kind of analysis that does a transform on a system, and you assume the transform is somewhat reversible, so you can break down a signal into its components. You can do something to those components, and then you can reassemble those components. We're making an inherent assumption that the system is nonlinear, is linear. So the reason that we have to ultimately consider nonlinear processing, there are several reasons, but primarily the real world is a nonlinear system. Now, a lot of times you can make linear assumptions, but as soon as you do, you lose some information. Secondly, nonlinear analysis can provide much greater information regarding the dynamics of the measured system. And so dynamics refers to what are the governing rules of the system from which the signal originated. So to say that we would use nonlinear signal processing because all of our other analyses have come up short is not necessarily a very good reason, although it is a reason. Secondly, if we suspect our signal comes from a nonlinear system and we just want to know more about it, that's a better reason. And finally, if we know our system is nonlinear and we want to somehow differentiate measurements from different system conditions, that's also a very good reason. So nonlinear versus linear. Nonlinear signals tend to come from nonlinear systems. And nonlinear systems have governing equations that have nonlinear terms. And nonlinear terms would basically be sinusoidal terms, exponentials, logarithmics, and so on. The input-output relationships do not obey superposition. And one of the hallmarks of a nonlinear system is that small changes can be amplified or vice versa. So you may, some of you may have heard the statement, a butterfly flaps its wings in the Middle East and it creates a hurricane in the Gulf Coast. So that's the kind of thing that can happen with nonlinear systems and chaotic systems, is that you have small changes or small differences in initial conditions, and that makes for a very big difference in the ultimate outcome and behavior of the system. So a simple nonlinear system might be y is equal to x squared, where x is the input and y is the output. And if we input a into this system, we get a squared. If we input b, we get b squared. But now if we input a plus b for x, we get the square of the sums, okay, which is a squared plus 2ab plus b squared. That's not equal to the sum of the outputs of the individual inputs. So basically, this system fails the test of superposition, meaning it is a nonlinear system. A little more complicated system is a damped driven pendulum. And so here, theta and omega would be the angular position and velocity of a pendulum. And so obviously omega is the first derivative of the position with respect to time, the angle with respect to time. And then we have a relationship between the acceleration, the angular acceleration, and the input, or the angle, the position, the time, and the velocity. So basically B is a damping constant, K is a driving force term, G is the force of gravity, and L is the length of the string. So when you did your freshman physics class, you probably neglected these latter two terms, and then you probably also made the assumption that for small angles, the sine of theta is approximately equal to theta. If you do that, you turn the pendulum into a linear system, and you get the standard solutions for pendulum motion that we get in the freshman physics class. But in fact, often theta is not small. And often there is a driving force, and often there is a non-negligible damping constant. So basically what happens is, depending on the values of B and K and the initial conditions, this system can have very different modes of behavior. And it's nonlinear because of these sinusoidal terms. So looking at three modes of behavior when we make the first assumption, where the sine of theta is approximately equal to theta, so theta is going to be very small, we see that we get this kind of behavior. When we go ahead and allow the system to become nonlinear, in other words, allow it to such that you don't make the assumption that the initial angle is very small, but you're not taking into account the damping or the driving. Then you get this kind of figure B. And then figure C represents what happens when we have specific choices for K and B. And we can see here the pendulum motion becomes highly chaotic. So this would be representative of something like that water wheel that we saw in the video. So initial conditions and parameters alter the pendulum behavior significantly. So in those three cases, the first one, we had an initial angular displacement that was very small. We did not have a driving force, and so you can see the behavior was linear. When we let the angle get larger and we still have no driving force, the behavior was nonlinear, but it was still very regular and repetitive. Finally, if we keep the small angle, but we now add a driving force, we can see the behavior of the system becomes very chaotic. So one way to visualize this is to look at what we refer to as state variables are. So what are state variables? State variables are the sometimes measurable, sometimes not measurable variables that play a significant role in understanding the system. So in the pendulum problem, the state variables would be the angle of displacement and the velocity of the angular velocity of the pendulum. So if we do a plot in phase space and we look at velocity versus angle, if we have no damping, then what we find is if we plot velocity versus angle, we get a circle. And so this phase plot is sometimes referred to as the attractor. And in this particular example, the attractor is a circle, sometimes referred to as a limit cycle. Basically, it's just going to be limited and it's going to be cyclical and have the following characteristic behavior, where you just basically trace through this phase plot. As time goes on, you just trace through this phase plot over and over and over. If we now introduce the damping, then what happens is we find that the oscillations become damped. So if we look at angle versus time, it looks like this. If we look at velocity versus time, it looks like this. And so now if we plot velocity versus angle, we can see that there is sort of something that sort of looks like a spiral that ultimately approaches a 0-0 position. So basically, as time goes to infinity, this phase plane diagram is tracing out this curve, and it's going to approach this node at 0-0, and that's considered a stable node because it's not going to, once this motion has damped out, there's nothing driving it. It's not going to increase in its oscillation behavior. So the phase plane plot looks stable because you are approaching a stable node. So both this and the previous plot are considered stable. This one would have a limit cycle where you're not really going to leave this circle. This one would approach a stable node where you're not really going to have any deviation from a curve like the one shown. So the phase space plot is going to give us important information about a system based on the signals coming out of that system. Nonlinear systems can have really complicated phase space plots, but a lot of times we don't have access to all the variables. So for example, you may know that a process is going on, but you don't necessarily have access to what all the variables are. So you can't really know the dimension. So the next lecture will be concerned about looking at ways to recover or at least estimate the phase space of a multidimensional system from a phase space plot.